Hi everyone. I want to talk to you a little bit about the color test, microcrystalline test, the IR spectroscopy, and this kind of stuff lab. And I'm not going to get into the technical details of how you're going to split up the work or do it over 2 days or this kind of stuff. I'll leave that for your TA. But basically, I just want to go over a little bit about how this lab is working and what we are actually doing. And to do that, I just want to go through each section of the lab briefly and talk a little bit about the chemistry, or in the case of the IR, about how the IR works or things like this. So the first thing you're going to do is the Marquise reagent field test. And here is an example. It may not be the exact same field tests that we have available, or we may just have Marquise reagent available, which you can buy it in a bottle from a chemical supply company. But basically, this is what a field test would look like. And what this contains is formaldehyde and concentrated sulfuric acid. So needless to say, this is relatively nasty stuff, so be careful with it. That being said, it can change different colors with different drugs. So with ecstasy, maybe it'll turn purple. With meth, it'll turn black. And well, it looks like heroin and morphine turns purple, ecstasy turns black, and meth turns this brown color. So it can be finding these aromatic rings. And how this works is basically an electrophilic aromatic substitution reaction where we protonate the formaldehyde, and then this makes this extremely electrophilic, and it can attack the ring, and you can have a second attack, and you end up with this system. And what you'll notice here is we have this double, single, double, single. Now this plus charge conjugates this system, and you go from something that is white to begin with, acetaminophen, and you turn it into something that is colored because you have this larger conjugated system available to you. So essentially, this is how the Marquise reagent works, and I understand this is not great detail of this type of chemistry, but if you're taking organic, you won't get to a reaction exactly like this, but you won't get to electrophilic aromatic substitution reactions until the second semester. So that's basically how it works. So for obvious reasons, we're not going to be able to give you things like amphetamine or methamphetamine. So instead, what we're going to use is Mucinex. And Mucinex, again, has this aromatic ring. And this aromatic ring is capable of electrophilic aromatic substitution, and therefore you can combine two of them. Here you have an interesting question of which place is the substitution going to occur at. My guess is this one, but we won't get into that here, but you can see a color change. So basically you're going to look for a color change. The take-home message here, there's kind of a few things that are take-home messages. One, this is convenient because, you know, a police officer could have this in their glove compartment or whatever, and they could test something found on a suspect relatively quickly and get a color change. And there is some differences in colors for different drugs, so it is possible for this to work. That being said, because it works with aromatic rings, and I'm not saying it works with all aromatic rings, but because it works with aromatic rings, it's hard to say, you know, what exactly you have, although it's probably unlikely that somebody's carrying around a little baggie of Mucinex active ingredient. But that being said, it is reactive to things that are not those drugs. So there is a reason that we do things like GC and GCMS after we have this preliminary information from these field test kits. So another color test that we're going to do is the ferric chloride test, which is shown here. In the ferric chloride test, we can actually test for phenols. So a phenol is an alcohol group directly attached to a ring. And basically what this allows us to do is take iron 3 chloride, or ferric chloride, which is a yellowish color, and it turns into a molecule like this, which depending on the concentration can be a purpley color, or if it's a really dark purple, it'll appear almost black. And basically when we do this, we have this phenol group can attach one time or two times or even three times, and you might end up with some complex mixture, and then you might get, you know, 3 HCl's if it attaches 3 times. So this is basically how this is going to work. Said another way, this phenol group is slightly acidic, and it can actually lose its proton and then coordinate in this way with the iron complex. Now here, not a tremendous amount of drugs of abuse have phenol groups that are active to this, but something like propofol, for example, could be detected in this way. In our actual lab, you're going to test just phenol, which actually can be used as a drug by people like bodybuilders trying to lose weight because it's kind of poisonous and it raises body temperature. I would strongly not recommend doing that, but it can be used in that way. So ferric chloride allows us to test for phenols. So we have these two tests. We have the Marquis reagent test, and we can test for different drugs, and we have this ferric chloride test, and we can test for phenols. The next type of test that we're going to do is something called a microcrystalline test, and none of these are drugs, but in the microcrystalline test, you're actually going to look at the powder, the crystals in the powder, and see if there's a difference. So in this case, some crystals may be needle-like. Okay, some crystals may look like this, and some crystals may be like these squares. And you can see that under a microscope, you could easily identify the difference between these, even though each of these may be a white powder. Now here, this looks a little bit yellow, because it's just a picture I could find on the internet, but you get the idea. Obviously, if one powder is yellow and the unknown's yellow, it's going to be relatively easy to tell. Sometimes it is helpful to look at the powder itself, because not all white powders look exactly the same. So sometimes, even without the microscope, you can tell that there's a difference in the shape of the crystalline structure, and then when you see it under the microscope, you can really strongly tell that there's a difference. Sometimes the needles are so large you could actually see them, okay, in the sample with the naked eye, and you don't actually need the microscope. But here, what you're going to do is you're going to look at several different powders, both just visually with your eyes and also under the microscope. And what you're going to do is attempt to determine which powder is the unknown based on both your visual inspection and your microscope inspection of those different crystals. And this is relatively important because a microscope is quick and easy, right? There's not a lot of sample prep. You just pour a little bit on the slide, essentially, and then look at it under the microscope, and it can give you a good idea of what you're looking at. Then you can do further testing with the GC or the GCMS, as we discussed before. All right, the next thing is hair and fiber examination under the microscope. And this is to give you a little bit of a flavor of some of the things that forensic scientists do, but probably this isn't done by a chemist. And some different types of hairs and fibers have different characteristics. So for example, this is a cat hair, this is a dog hair. You could tell the difference between them just by the structure underneath the microscope. This is a human hair, and this is a red human hair. They still both look like the human hairs, okay, but they're obviously different colors. So this is going to be what you're going to do in this portion. The other thing you could have is you could have fibers. So this is a denim fiber here from jeans, and you can see it looks quite a bit different than the hair sample. Sometimes, I mean, obviously if it's a blue denim fiber, you're probably not going to think that it's hair, although it could be dyed hair, but you could tell the difference between the fibers and the hairs because they have unnatural structures. Sometimes a fiber will be, threaded, or it'll be wrapped around another fiber or a coil or something like this, and you can tell the difference. Under the microscope, although you may not be able to tell just by looking at it, there are some very distinctive differences, and again, you could then do further analysis. So for example, let's say that a hair had a root in it and a forensic investigator wanted to do a DNA test to see if a suspect could be identified. Well, if someone looks under the microscope and they find it's a cat hair or a dog hair, and an experienced person, my guesses would know very quickly that that wasn't a human hair. They're not going to bother to do a DNA test on it to find out that it's a cat. So this is just one very overly simplified example, but it gives you an idea of the potential use of this, because you don't want to waste resources doing a DNA test on a hair that doesn't belong to a human. And you could think of similar ways in which, like a blood sample, for example, although we're not going to use blood samples, if you could figure out that it's, a dog's blood and not a human's blood, or some other animal's blood and not a human's blood, you're not going to spend time analyzing it if it doesn't belong to a human being, depending on the case, of course. All right, so that's basically the hair and fiber analysis. Again, you're going to use the microscope to do this. Finally, what you're going to do is IR, or infrared spectroscopy. And FTIR is basically going to use a light source, and that light source is going to be of infrared radiation, which is slightly lower in energy than visible light. Infrared radiation is actually what you'd find in a heat lamp that would keep french fries warm at a fast food place, something like this. And what it does is it causes molecules, covalent molecules, to vibrate and rotate, and this motion can cause a rise in temperature because the average kinetic of the energy of the molecules increases. But in an infrared spectrometer, and I will leave a link in the description to a video of someone who's much more knowledgeable about this than me explaining it really well, but basically what you're doing is you're using an IR light source. This IR light source is then going through a beam splitter. And a beam splitter is, you can kind of think of it as half glass and half reflective. So half of the light goes straight through, and half of the light is reflected. So half goes this way, half goes this way. One of these two mirrors is stationary, which means the waves come back in exactly the same condition that they were reflected in, and it's a certain number of wavelengths away, so they come back exactly as they were reflected to it. This mirror moves, and this mirror moves in and out, which means that you can, when these beams are recombined here, you can have them in phase, which means you essentially get back, in a perfect world, the exact same wavelength and amplitude that you started with, or if this moves half a wavelength over, they'll come in out of phase, and you'll actually have no light going here. And in this particular example, what we have is one wavelength of light, right? We have a constant wavelength of light. But in reality, IR isn't a single wavelength. IR is a whole bunch of wavelengths measured in something called wave numbers, which is centimeters to the -1. You may be familiar with hertz, which is seconds to the -1, which is how many crests or whatever, how many waves pass in 1 second. Centimeters to the -1 is how many waves you would find in 1 centimeter. And we're going to go here between about 4,000 and about 600 if we use the ATR attachment. So this is basically what's happening. So all the wavelengths of light are coming in, they're being split. This moving mirror is moving back and forth, and you're going from regions of constructive to destructive interference. Then all of this light passes through the sample, and some of these wavelengths may be absorbed to cause vibrations and rotations in molecules. And then when it goes to the detector, you're no longer receiving those wavelengths of light. Using an advanced mathematical application called a Fourier transform, you can actually measure which ones of those wavelengths of light are missing, and you can essentially figure out the absorbance of your molecule. So what a molecule does is, what a molecule energy level has is, here you'll see these electronic energy levels, which you have learned about in general chemistry, like N equals 1 and N equals 2 and things like this. But there are also these vibrational and rotational energy levels, which are much smaller energy gaps, and therefore relatively low energy radiation, like infrared radiation, can be absorbed by covalent molecules. Again, this is what keeps the french fries warm at the fast food place, but it can also be used to identify things. And in IR, if we were taking an organic chemistry class, what we typically use it for is to identify functional groups. So if you do an organic reaction and you change from an alcohol to a carbonyl, for example, you'll go from an OH, which is a broad peak here, to a C double bond O, which is usually a pretty strong stretch here. So you can actually identify functional groups. However, there's another use of IR. So what I want to show you here is acetaminophen, okay, which is found in Tylenol versus methamphetamine. So you can see these molecules are a little bit different. If we look at the methamphetamine, we can see that it's going to have an NH, which is probably, here, it's hard to tell, and it's going to have CHs and a CH aromatic. The NH you're not really seeing here because this is basically secondary compound, and for whatever reason we're not really seeing the NH over here. So this is probably CH aromatic, and this is probably CH aliphatic. So basically we have the aromatic ring, those CHs you're going to find here, and these non-aromatic ones you're going to find down here. All right, so that's basically what we're going to see. If we look at acetaminophen, okay, which is here, let me make this a little bit smaller so that we can see it. We have a functional group, which is an OH, which is this broad peak here. We have the aromatic CH here. We have the aliphatic CH here, just below 3,000. And we also have a carbonyl peak, which for whatever reason isn't particularly strong in this one, probably because it's an amide, but we're going to see it right here. So this is basically what we have in these two molecules. And this is how we would use this in organic chemistry. And in organic chemistry, we'll actually tell you, ignore this region below 1500. This is the fingerprint region. But there's another way to use IR. And there's a way to use IR that forensic scientists might use, where you actually use a computer to determine how close these spectra are to each other. And you'll notice these spectra aren't very close. But even in the fingerprint region, this is going to be unique for each molecule. So even if you took acetaminophen and you put a methyl group here, which may not be an easy thing to do, but let's just say we did that, the IR spectrum would be very similar, but it wouldn't be exactly the same. And this IR would allow you to distinguish those molecules if you used a computer to compare the two spectra. So you may say, well, why not just use a mass spec? Okay, that's probably going to give you better data. You can make a case for that. Well, yeah, sure, it will. But at the same time, an IR generally requires relatively little sample prep. As you're going to see, we use something called a diamond ATR attachment, and you literally just take the powder and you put it on there and you clamp a little thing down and then you hit run. And within 30 seconds or so, you get your IR spectrum. So it's relatively quick and easy. There's no sample prep. You don't have to do anything. You just take the powder that you caught on the suspect someone confiscated from the suspect. You put it on the IR. You compare the fingerprint. It can be very useful. So then you might say, oh, that sounds great. Why in the world would you ever use a GCMS? The sample prep is going to be longer. The instrument costs more. It's going to take longer to run it, so on and so forth. But the truth is, for IR, you need a pure sample. So it doesn't need to be 100% pure, but you need a relatively pure sample. You're not going to take a blood or urine sample for somebody and look and find metabolites of cocaine in it, because all you're going to see is probably the water that is the basic basis of the sample, right? The solvent, if you will. So basically, both have their uses. If you have a pure sample, you have a baggie of something, IR can be very useful. And the fingerprint region, even though we tell you to ignore it in organic chemistry, is very useful. If you have a complex mixture where you need to do some type of extraction using solvents and so on and so forth, IR may not be so useful in that case. So I hope this gives you a little bit of an idea of what you're going to be doing in the lab for the next 2 weeks. I do want to point out that I'm not getting into the technical details of exactly what samples you're going to run and things like this, but I wanted to give you a broad overview of what you're trying to accomplish, what the different tests, the color tests, what we're trying to figure out, and what types of molecules they work with. The microcrystalline tests, how to look at the sample both visually and under a microscope to see if there's some similarities or differences in the crystal structures that might give you some indication of what is what. The hair and fiber analysis and how that might be useful and save researchers time from running DNA tests on dogs and cats, for example. And finally, a little bit about how an IR works, why molecules absorb IR, how we use IR in organic chemistry, and finally how IR can be applied in forensics. All right, so I hope you found this video a little bit helpful, and it gives you a little bit better of an idea of what you are doing in lab over the next 2 weeks.